There we go. Recording is on. All right, so we are pretty much done with the graph topics, because we talked about Dijkstra's algorithm. We talked about the A-star algorithm. You have both assignments up and running. I think they're both due on Wednesday, so you still got about 2 days to work on those. So we can now proceed to topics after your graphs. We got two topics for you. I got two topics for you guys to choose from. We have time complexity, which is the big O notation, which is not really just big O. Okay, there's quite a bit more to it. And then we also have predicate calculus, which we can use prolog and do some fun stuff with. If you ask me which one is more relevant for your future, for other classes that you'll be taking, I would say time complexity is probably more important. If you ask me which one is more fun, then it's going to be predicate calculus, because you can use prolog and you can do all kinds of stuff. We can talk about the family tree of the Simpsons, and yeah, it's going to be fun. So, your choice, your pick. Okay, sure. Question. So let me finish the poll first, and then we'll get back to your question. So what do you guys want to do next? Predicate calculus? You guys don't care about the complexity, time complexity? Okay, we might have time to get back to time complexity. Yeah, go ahead.
Is it wrong that your final solution, after you've gotten everything, if you don't have an edge to a destination, if you have one of your destinations?
I think both graphs are solvable.
They are, but I don't have an edge to one of the destinations.
Oh, that's perfectly okay. Yeah, because if there are multiple destinations, then each vertex will only have a path to one of the destinations. So you're not guaranteed that you would go to every single destination, because all the vertices, they consider one of the destinations as the closest. So you can't have a destination that has no solution edge you're leading to it. Yep. So that's entirely possible. All right, well, since we all kind of voted on predicate calculus, we'll go ahead and start with predicate calculus. All right. And let me just kind of bump up the font size a little bit. All right. So AI, is a big topic these days. In fact, just last Friday, I think, I went to a meeting with industry. It's an advisory committee meeting with all the industry leaders, in the Sacramento region. And someone decided, that maybe we should pursue AI and ML, machine learning, and all the other cool stuff. As it turns out, the employment rate of ML specialists and data science specialists within this region is pretty small. Because I think that's, I mean, as interesting as those topics are, they are not as applicable as something as practical as COBOL programming. Okay, you guys are all silent because you don't know what is COBOL programming. Does anyone know what is COBOL programming? More or less? What is the context of COBOL? Go ahead. Yeah, mainframe computers, which is not how IBM wants to call those computers anymore, because when people think of mainframe computers, this is the imagery that people would come up with. So this is kind of like a digression from what I really wanted to talk about. So if you look at mainframe, this is probably what most people think of, which are like this, or worse yet, mainframes from the 1960s. I think that's what most people are thinking of, black and white pictures, not even color, not even colorized. Okay, it's just black and white. So Sacramento region has a lot of COBOL, programming jobs open because the state government is here. So the DMV, the Department of Motorized Vehicles, BOE, the Board of Equalization, all of those state agencies, they still run their applications on IBM enterprise computing platforms. That's the new word of mainframe, is enterprise computing. And because nobody from a university like they don't teach this stuff at a four-year university. Okay, period. So that means the number of people who can get into the state and start to pick up these programming, update all the software and whatnot, is a very limited pool of people. Wells Fargo also wants people who can program your mainframe. And locally, I think the city of Roseville also use mainframe computers to keep track of their stuff. So you have basically all of these agencies, companies, and organizations trying to poach employees from each other. And there's a big shortage, and that's why I mentioned your mainframe computing. But getting back, so if you want to roll back time to the 85, 86-ish, that is when Prolog came along because it is the programming language for AI type of programming back in those days. AI in this sense has nothing to do with neural nets. This is more like symbolic processing. So what I will do is I'm going to introduce, the basic statements. So we'll go with the examples first, and then we'll go back and talk about the theory a little bit more. So if you want to specify that Luke Skywalker is a Jedi, this is how you would state that. You would basically use a predicate. So is a Jedi is the name of a predicate, okay? And as I have explained before, a predicate is basically a function that returns true or false. You give it a parameter, and it will come back either as true or false to tell you whether, in this case, Luke Skywalker is a Jedi or not. But since, in this case, I have a period at the end of this particular sentence, it means this is a fact. Okay, so I'm no longer asking whether Luke Skywalker is a Jedi or not. I'm stating that Luke Skywalker is indeed a Jedi. So I'm affirming a true statement. Is that okay? So this is how we can input facts into the system. The other way to do this, which is the long form of this thing here, is this one here. So the way we read this is kind of funny because this is actually a conditional statement. It is an if-then statement, except you read it backwards. This says true implies Luke Skywalker is a Jedi. That's kind of how you read it. The way that is forward reading like this is a Jedi Luke Skywalker is implied to be true. That's how Yoda would have said it. Okay, that's just a joke. Because Yoda talk is like moving the things around a little bit. Okay, so this is the longer form of this. So now you can also formulate rules. Now this is where the fun begins. So you can basically define what is a proper Jedi. So in this case, okay, so I'm just going to highlight the sentence first, and I think you guys will kind of get a sense of what it is about. So is a proper Jedi, this symbol here can also be interpreted as only if, okay? So X is a proper Jedi only if X is a Jedi, the comma is a conjunction, and X owns Y, and Y is a lightsaber. In other words, in the universe of predicate calculus, anything that starts with a lowercase is what we call an atom. Okay, it can be anything. So the atom itself, a particular name, an identifier, has no type associated with it and has no special property until you basically say blah 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 is a lightsaber, blah 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 is a Jedi, blah 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 is a Sith, and so on. Otherwise, there's nothing related to a particular name, which is also called an atom. Are we doing okay so far? Okay, so if you want to name a few things as a lightsaber, this is how you can do this. You can now say Anakin Blue, which is how I call the blue lightsaber that Anakin created, is a lightsaber. So this is how you can state a fact within a prolog program, is to basically say, make sentences like these. Do we have any questions? Now, the other thing about SWI Prolog is there is an online version, so you don't even have to install anything to play with it. So you can look up SWI Prolog web or web-based SWI Prolog for sharing. There we go. Swoosh dot swiprolog.org, and we can sign in. We can also just kind of go ahead and create the program. So we can, based on create a program, there we go. And now we can start typing the program. So let's go ahead and type in a few items here. So we can say is a Jedi, and we'll name a few Jedis here. So Luke Skywalker is one. And who else do you want to name as a Jedi? Name a few. Yoda. So you have to be careful because an atom, like Yoda, Luke Skywalker, and so on, they must start with a lowercase. They cannot start with the uppercase. Only unbound variables can start with the uppercase, and I'll talk about what is an unbound variables later. Yep.
Is that why methods are usually start with lowercase?
That's a different thing. So the camel casing, has a different origin. I believe Prolog predates C++ programming. It does not predate C, but I think it predates C++. They came around at about the same time. All right, so we can name a few more. Maybe Obi-Wan Kenobi. Okay, so how do you want to spell it out? Kind of long. Obi-Wan. Obi-Wan. Is that the correct spelling? I think. Okay. All right. Okay. Only with these three facts, I can play with it already. Okay. We can ask the engine, like there are two kind of things we can ask. So you can ask something like, is a Jedi? And we can confirm one. Okay. We can ask is Yoda a Jedi? So basically, this is what you're asking: is Yoda a Jedi? When this is a query, and I have to press Control Enter and it comes back as true. Okay. Well, that's hardly surprising because I stated that Yoda is a Jedi, and then came around to ask, is Yoda a Jedi? The answer is yes. Okay. Or in this case, true. Not a whole lot of fun, right? But we can also ask some other questions. Okay. So we can now ask, is a Jedi? And now this time we can name a Sith, okay? Sidious. Sidious. And Control Enter to ask the question. Cannot run. Okay, so why is that? I think it's because Sidious is not a defined atom. But let me ask Obi-Wan first. Cannot run due to a syntax error. And it has to do with, because I can only ask one question, it is still okay. So this will work. Sidious. Control Enter, and it says it is false. Sidious is not a Jedi. In fact, if you ask it anything other than these three, it would not be a Jedi. Now, the other thing you can also do with a query is you can ask, who are Jedis? So this time, this X here is starting with the uppercase X. So anything that is uppercase is interpreted as a variable. So this time you're not asking to confirm a particular atom, whether it is a Jedi or not, or he or she is a Jedi or not. You're asking what are Jedis within the system. So when you press Control Enter, it will tell you Luke is a Jedi, Yoda is a Jedi, and Obi-Wan is a Jedi. Okay? So somewhat interesting at this point. With ancestry, it is a little bit more fun. So we can also shift gear to talk about ancestry. But so far, this is what we have at this point. Okay, so you can now define other things like is a lightsaber, because now we need to establish what are the lightsabers within this universe. So we have Anakin Blue, Anakin And how do you spell Anakin? Anikan, Anakin blue. Okay. So now we're defining, this is a lightsaber. And now we can define, who has what. Okay. So we can now define Luke Skywalker has Anakin blue. Okay. And you can also define a bunch of other things, but we'll go ahead and define the rule first. So the rule, getting back to this module, spells out is a proper Jedi X only if X is a Jedi, X owns Y, and Y is a lightsaber. So you need all of these requirements in order for X to be a proper Jedi. So a Jedi or someone who practiced, who used to be a Jedi but has lost the lightsaber is no longer a proper Jedi. Okay, so we can go ahead and define this rule. So now we can say is a proper Jedi. So it reads the other way around. Remember, when we are programming, it's mostly Yoda talk. So things are not in the right order if we are to spell it out, just straight up. So now this time we have to use this symbol here. And remember, if you want to read from left to right, in other words, if you're not Yoda, this symbol means only if, which is the reverse of if. In other words, the right-hand side implies the left-hand side and not the other way around. Is that okay? All right. So this is saying, X is a proper Jedi only if. So the first thing is X has to be a Jedi. Is a Jedi X. That really does sound like Yoda talk, doesn't it? And then the second one, remember the comma is and. So now we have to say, X owns one particular thing, Y, and Y has to be a lightsaber. Yep.
Do we have own defined as has?
Oh, right. Sorry. So we can change this one or we can change this one. We can change has. Forgot that I used a different word to describe ownership. It's a lightsaber, and this has to be Y. All right, so now I have just defined a rule which says X is a proper Jedi only if X is a Jedi and X has Y, or X owns Y, and Y is a lightsaber. So now we can ask that question. Okay, so we can now ask the question of is a proper Jedi X? So tell me all the proper Jedis within this universe. So Control Enter starts the query, and it comes up with Luke Skywalker. If I click next, that's the end of it. So it knows how to find, quote unquote, the answer in a kind of interesting way. Are there any questions at this point? Okay, so I do have a question, which is what is predicate calculus? How does it relate to propositional logic? The answer is simple. Predicate calculus can have quantifiers, but propositional logic does not have quantifiers. Okay, that's the main difference between propositional logic or propositional calculus and predicate calculus. In predicate calculus, we have quantifiers. But you look at this and go like, I don't see any quantifiers. I don't see any for all, and I don't see any there exist, and so on. So what is going on here? So as it turns out, there's a difference between X and Y. X appears on the left-hand side of this particular symbol, and Y does not. Y is only appearing on this side here. So the quantifier is implicit. Any variable that is appearing on the left-hand side is a for all. Okay, so this is basically saying for all X within this entire universe. Okay, for all X is a proper Jedi only if blah blah blah. The Y on the other hand does not appear anywhere on the left-hand side, so the Y is existential only. So we are basically, if we are to add quantifiers to the statement. Now we are basically saying for all x, x is a proper Jedi only if x is a Jedi, and there exists y such that x has y, and y is a lightsaber. So y is existentially quantified, but x is universally quantified. Is that okay? So by adding quantifiers, the trick that we used to do, which is let's boil everything down to CNF and do the resolution until we get a contradiction, that doesn't quite work anymore. Okay, and the reason why it doesn't quite work anymore is because we can have recursive definitions. So this particular example does not lead to any type of recursive definition. So let's go ahead and take a look at a different example where we can end up with recursive definitions. And that is when the family tree of the Simpsons comes in handy. Simpsons family tree. And there are quite a few online, and I think this is the one that I usually use. It's a pretty extensive family tree for The Simpsons. And all right. So we'll start with the characters that most people know. So we'll start with Bart, Lisa, Maggie, Homer, and Marge. Okay? So how do we express these relationships? So there are a few things you can do. I mean, you don't have to do all of this, but if ancestry is the only thing you want to track, then we can go for the minimum in order to do this. So we go back here. Now we erase this program, and then we say we can have a parent of. Okay, so we can say parent of, and now we can define the facts. Who is whose parent? So now we can say, let's see, the parent of, okay, I'm just trying to decide which way to name the characters. So the parent of Bart is Homer. Okay, well, that seems to work. So now I'm stating a fact. Okay, remember, if you use a dot at the end, um, and without anything in between, without the only if, you're now stating a fact that Homer is indeed a parent of Bart. And now we can use the other one, parent of, we have Lisa, Homer, and you can also define the mom, who's Marge. So Marge is, the other way around. Marge is also a parent of Bart, and so on. So how do we differentiate between a father versus a mother? You can define gender. Okay, so the way you define gender is male, Homer, and female, Marge, if that is important. So in the example that I'm trying to illustrate here, gender is not important. So I'm not going to define the gender for every single character, but parent of is important. All right, so let's go back to the family tree, and this time I want to see who is a parent of Homer. So Homer's parent in this case is Abraham Simpson. Okay, so we can put Abraham or Abe into the example here. So now we can define parent of. This time we have Homer, and then Homer's parent is Abe. And we can go all the way up. Okay, so we can look up who is Abe's parent, Orville. How many of you already, how many of you are familiar enough of the family tree that you can actually, you know these names already? Nobody knows who's Orville? Me neither. Okay. And then we can go up. Orville's parent is Udell Spunky. Okay, so we can say Spunky. So parent of Orville is Spunky. And let me see how far I want to go because I want to establish who is whose cousin eventually. Okay, so we have to kind of go up and then go back down again if we want to find all the cousins. So we have Spunky, and then Spunky's parent is Horatio. Horatio. But that family tree is, yep.
You made a mistake. His father wouldn't be Spunky, it'd be Ulta.
I followed the wrong side of the family.
That's his uncle.
That's his uncle.
And you see the M for marriage?
Hmm?
You see the M for, like, between a couple, there's the M sign? So
Mm-hmm.
Orville would be, Orville's parents would be Happy and Ulta.
So Orville is here. Oh, okay.
So M implies they're married. So Ulta and Happy are his parents. Whereas
Cannot.
Spunky is his uncle.
I don't see.
So go to the left of Orville.
Mm-hmm.
And go up to the next generation, right above him, and go all the way to the left. See Ulta and Happy?
Mm-hmm.
Ulta is his actual father, not Spunky.
Okay, Otut and Happy has these four children. One of the children is Orville. Orville married Yuma, and yeah, so Abe is their offspring, and then Abe married Penelope, and Homer is the offspring.
Yeah.
So I think Orville is still along the ancestors tree of Bart.
Yeah, but I think the issue was Spunky.
Oh, right. Okay, gotcha. So Otut is the correct ancestor, not Spunky. You're correct. Okay, because of these two marry, and these are the offsprings. Okay, thank you. So we update this with Otut.
Huh. Came back at the Simpsons family tree.
Hmm?
I didn't expect that.
You never know where this class is going, right? It's like, what are we talking about again? All right. Okay, so even with only this much, okay, we can now define something that is recursive, which is the ancestor of relationship. Okay, so we want to define who is an ancestor of whom. So let's go ahead and define that. Ancestor of. And this one cannot be using the atoms because I don't want to hand enter all of the ancestry relationship because that's just a lot of work to do. And I should be able to programmatically figure out who is whose ancestor. So in this case, I can now define and say X is an ancestor of Y only if. Okay. All right. Well, because if this is a recursion, the first thing we need to think about is how does it end? Okay, when can we just say for sure whether X is an ancestor of Y without doing any type of recursion? That would be the first thing we need to specify. Oh, that would be pretty easy because if I can establish that X is a parent of Y, then X is also an ancestor of Y. And that does not involve recursion. Pretty easy to work out. Are we good so far? Okay. And now you can define another one. So the way you define alternatives is you just use exactly the same predicate name, and then you define it differently. So in this case, we can now define ancestor of xy. X is an ancestor of y only if. So this time we have two choices because we can put the recursive call first, or we can use the non-recursive call first. So let me explain what I mean by that. You can say X is a parent of Z and, and ancestor Z is an ancestor of Y. This is one way to specify that. And the other way is to reverse the order of ancestor of versus parent of. So let me fix the spelling here because it's supposed to be ancestor of and not just ancestor. And I'm just checking the spelling here, making sure everything is okay. All right, looks okay to me, even though that has a underline next to it, or underlined ancestor of. Okay. All right. So at this point, we have the recursive call after the non-recursive call. In other words, we first want to make sure that we can find a z such that z is an ancestor of x, and then we do the recursive call and say, well, can we establish the z? Oh, I reversed that one, didn't I? And then we have to ask, can we reverse that so that y is an ancestor of z? Okay, I didn't have it reversed. That is correct. All right, so are we ready to kind of check out whether this one works or not? We'll start with something simple. So we'll say, who is a parent of Bart? Okay, so this is basically asking, um, who is a parent of Bart? And the correct answer is Homer and Marge. So that should be two answers to this particular query. And clauses of parent of are not together in the source file. Okay, so it wants everything to be together. Okay, we can just move a few things, cut and paste. So once again, the gender part is not important. All right, so we'll go ahead and check this again. So it has Homer as one parent of Bart. It also has Marge as the other parent of Bart. So those are all correct. Are we good so far? You can also flip it around and you ask, who are the direct offsprings of Homer? So to ask that question, you basically flip it around and you have the child as a variable, and then the parent is spelled out. So you can now spell the parent as Homer. Control Enter. Bart is one offspring. Lisa is the other offspring because I did not enter the third offspring of the family. Are we doing okay so far? So you can query. Question?
One quick question.
Yeah.
So for parent of X, why do you have Y and Z?
You mean here?
Yeah, both lines.
Because I need to do the recursion. So that means, I need to find a parent of X, and then, I have to establish also that Y is an ancestor of Z. That will make Y an ancestor of X.
But the first line says parent of X is Y.
The first line?
Yeah, like
The line before?
Yeah.
But this one is not recursive. This one is recursive. And in the recursion, I need Z as a variable that links the ancestor of with the parent of. Okay? So now we can start to play with ancestor of. Okay? We'll try something easy first. Okay? So instead of just parent of, we can now just ask ancestor of. Ancestor of. So Homer is an ancestor of Bart, okay, and of Lisa, and that's it. Okay, seems to make sense. Everything is good. And now we want to extend the family tree just a little bit, and we want to see if we can include other offsprings of Hut, Ohut. So Ohut is here. Unfortunately, there's no one of the same generation as Bart if we just added Ohut. So I think we have to go up another level, which is Howland. Okay, there we go. So Howland is the ancestor of Ohut. Because I want to get to these three. So, let's go back to, so parent of Ohut. Otut as a parent of what again? Um, Howland. There we go. And then we move down the family tree. So parent of, this time we have another offspring of Howland. So where's Howland? Otut, this is Howland, and we need to follow the tree down to here. So it'll be Lou Simpson. Okay. And then after Lou, we have Twyla. Okay. And then after Twyla, did I misspell the name? Twyla is a Y, not an I. All right, get tracking down to Furnice, Fernice. And then we have Pomona. And then finally we have the people of the same generation as Bart. So one is Alberta, Hazel, and Violet. Okay, we'll just put Violet here. All right, so I think I got everything encoded. We'll find out. All right, so this time this is going to be a long list because I'm asking who are the descendants of Howland. All right, so we got Otut, Lou, Bart, Lisa, Homer, Abe, Orville, Twyla, Furnace, Pomona, and Violet. Okay, so we got all of the descendants of Howland. All right, so this is kind of fun because now you can see the power of the query and also how we can utilize rules so that we can infer things that are implied by the rest of the program. Are we still doing okay so far with this? So remember how we read this, okay? If the variables appear on the left-hand side of the only if, those are universally quantified. If it appears only on the right-hand side, it is existentially quantified. So when we read the second rule of ancestor of, we are really saying that for all x and for all y, x is an ancestor of y only if there exists z such that z is a parent of x and y is an ancestor of z. So the quantifiers are applied differently depending on whether the variable appears on the left-hand side or only on the right-hand side. And this is the one thing that is missing from propositional calculus, is we do not have quantification when we are talking about propositional calculus. Is that okay so far? All right. So now the big question is, can we find cousins? How do you define cousins? So this is a cultural thing because depending on the culture, some cultures track cousins differently depending on whether those cousins are on the mom side or dad side. They are called differently, and other cultures do not make a differentiation depending on whether it's from the mom side or dad side. So we're going to say that it doesn't matter which side, okay? So we just want to define, we'll just go ahead and define regular cousins first, okay? So if we just use the word of, this person is my cousin, what would be the implication of that sentence? Well, yeah, go ahead.
You have the same grandparents.
You have the same grandparent. Okay, very good. Or the same ancestor at some point, right? But it cannot be your immediate ancestor because otherwise your siblings will also become a cousin. But that really is just a scope problem. It's like, where do we find the common ancestor? Is that making any sense? So you can define, how about cousins that share the great grandparent? Would those be also be called cousins? Yeah, those are also cousins. So, so the general meaning of cousin means, just having a shared ancestor. Okay. So that means if that is the case, we can now define cousin of. So X and Y are cousins of each other, only if what? How would I define, the cousin of relationship? Based on what I just said, they have to share a common ancestor. How do we utilize the predicates that we have already defined so that we can determine whether X and Y are cousins or not?
Would it be if and ancestor of x and y, comma yx?
Okay, so we have ancestor of, okay, and what do we put in the parentheses?
The xy.
XY? Well, if Y is a cousin of X, Y is not an ancestor of X. So it's not quite, yeah, go ahead.
Is it XC and YC?
Yep, we need a third variable as the ancestor. So there has to exist a Z such that Z is an ancestor of X and ancestor of YZ. That is correct. Okay, so we'll check it out. Okay, so we'll check out. We'll ask you to confirm a few things first. So we want to check out whether Violet is a cousin of Bart. Okay, so cousin of Bart on one side, Violet on the other side, and then Control Enter to ask the query. The answer is yes. Very good. But then we'll also find some unexpected answers, okay? Well, I shouldn't say unexpected, because if I change the question and ask whether Homer and Violet are cousins or not, what should be the answer? This one is a little bit trickier. So if I go back to the family tree and I ask, is Homer a cousin of Violet? What would be the answer? Yes, they are, but they're not at the same level of the tree. There's a way to express that. Okay, you can see how Homer is at this level of the tree, but Violet is at the same level as Homer's kids. So there's a way to phrase this type of cousin relationship. What would that be? Okay, so the generalized way of expressing cousinship is there's a if cousin, and then you can also specify how many levels removed. Okay, so how many people are familiar with that particular way of qualifying, cousins? Okay, ish. Okay, well, we can look up the definition. So we want to look up the definition because I want to express, that kind of cousinship, correctly. Because right now, did I confirm that this is also a yes? Nope, I have not done that yet. So let's Control Enter, and it confirms that. It confirms that Homer and Violet are cousins. Well, they are indeed cousins, okay, but we can probably qualify that cousinship a little bit better. So now we look up your cousins, okay, cousins removed. Um, And just generally how we name cousins. Cousin chart, family relations explained. What is a cousin? Cousins are people who share a common ancestor that is at least 2 generations away, such as a grandparent or great grandparent. So it disqualifies siblings as cousins. Okay. All right. Well, that's easy to integrate into this query here. You and your siblings are not cousins because your parents are only 1 generation away from you. So that's basically just conventionally how we use the term cousins. But then we also have to look at this chart here. Great grandparent, and now we have great great grandparents, sorry, great grandparents, and then we have grandparents. So this one is first cousin twice removed, but relative to, oh, all the green ones. And these are second cousins once removed, third cousin. If this is me, oh, okay, I see. So everything is related to, in relationship with me. So that means the number removed is the difference in the tree level, and then the first, second versus your third cousin has to do with the generation. So if I add the if to the removed, then they should add up to be the same. Okay, I'm not sure whether I'm making sense or not. I know what I want to convey, but I just don't know whether it came out in the correct way or not. Okay, so if you look at this, this is second cousin. This is first cousin. So first, second, or third is basically how many, at which level I find the common ancestor. Is that making any sense? Okay, let me phrase that one more time. A sibling is not a cousin because we share the same parent. This is me. This is my first cousin because we share the same grandparent. This is a second cousin because we share the same great grandparent. This is a third cousin because we share the same great great grandparent. Okay. So the number first, second versus third has to do with how far do I have to go up the tree to find the common ancestor. Is that okay? So I need a way to specify, ancestor at a certain level. Does that make sense? Because in order for me to be able to specify, I only want to find, okay, for example, all my second cousin once removed, okay? And obviously, if the family tree is only this simple, it's not going to be fun. But assuming this is a more complex family tree, and I want to find all my second cousin once removed, I need a predicate that can help me identify, ancestor, but at a very specific level. Okay, so the question is, how do we do that? So we go back to this program, and then we define, another predicate with ancestor. So we now say ancestor n of. So this time we specify the 2 people, but we also specify the number of levels of ancestry that we want to enforce in this case. So n is going to be an integer, and we want to specify y is an ancestor of x this number of levels away. 1 being parent, 2 being grandparent, and 3 being great grandparent, and so on. So the question is, how do I specify this particular statement here? What do you think? Well, first of all, what is the non-recursive case? The non-recursive case is y is a parent of x, in which case n is going to be 1. Okay? So now we can say, oh, okay, wrong part, this part here. So now we can say n is 1, okay? You can actually write that, okay? It's not a comparison. It says n is 1 and parent of y, oops, xy. There we go. All right, so let's go ahead and try to read this out, just in English. It says y is the nth ancestor of x if and only if n is 1 and y is a parent of x. Okay, seems to make sense. Okay, so the first thing we want to do is we can try this out. So this is why I like Swish, because it's interactive. You can do something to quote unquote the database or the rules, and then you can just try it out and see what happens. So we can go ahead and change this query here. And we just want to start with confirmation. So I want to confirm that ancestor and of. We'll start with Bart and Homer, and they should be one generation away. And I just want to see if that predicate returns true. The answer is yep, it's all good. And now we want to check, if it is supposed to be false, would it tell me it is false? So there are a few ways to play with this because we can find who is the parent of Homer. So this is Homer and this is Abe. So we can now change the question just slightly and ask whether Abe is one generation, from Bart. And the answer is nope. Okay, seems to work. Cool. So that is our non-recursive definition of ancestor and of. So what do you think the recursive one is going to look like? Okay, so it starts with the same thing. I want to check if y is the nth generation, nth ancestor of x. All right, so how do we specify the only if, the right-hand side of the only if in this case? It's supposed to be recursive, which means somewhere within on the right-hand side, we have to reuse ancestor and of. Okay? But the problem is I need n to decrement by 1. Because once I confirm somebody, okay, so we can call that z is a parent of x, I need to now establish, because I'm using the same trick as this line here, except this time I'm counting as well. So the first part is easy, okay? We have to find a z such that z is a parent of x. Okay, that part is the same as that's 2 lines ago. And then we can now have to say m is n minus 1. So I need a new variable, m, because I cannot put n minus 1 into a query. That's just part of the syntax. It does not allow me to do that. So I need to specify an m, which is a existential variable. Now I can specify the recursive call, which is ancestor n of, and this time we have y. I think the other way around, sorry. So y is the ancestor of z, but the number of level is going to be m away. Okay, so are we doing okay so far with this? Is special because it can be seen as a comparison as what we have shown here, but it can also be instantiated. In other words, we can find out how many generations are between two different people. As long as one is the ancestor of the other one, it can actually do the counting for me and tell me how many generations the two people are away from each other. Are we good so far? More or less? Kinda? Okay, all right. So let's check this out, okay, because now I want to confirm that Abe is 2 generations away from Bart, but Abe is an ancestor of Bart. Okay, Control Enter. All right, excellent. It's true, and we want to make sure that Homer cannot be identified as 2 generations away from Bart. Control Enter. Excellent. And this time I will try, I think Howland, right? Yep, Howland. but I want to count the number of generations the Highland is away from Bart. So this time it's telling, oops, okay, press the wrong key, Control Enter. Ah, okay, arguments are not sufficiently instantiated. Okay, it should be a way to um, instantiate it. I just cannot. N is 1, parent of xy, m is n minus 1. Hmm. So that means the other one would not work either. If I put Homer here, it cannot resolve. Oh, it find. So did I lose track of the family tree somewhere? Okay, Bart, Homer, Homer, Abe, Orville, Orville, Howland. So they should all be connected. This is only one level away, so Abe is going to fail because it is this query that is not working. Okay, so it also explains what is doing. True when number is the value to which expression evaluates, which is n minus 1. Okay, so if I press this, then it complains about that too. So maybe it is not the is, maybe it's just equal to. Unify term 1 with term 2. Okay, so maybe it is just equal to. And the answer is false. If I give it 2, it is also false. So it's not the equal to. Unify term 1 with term 2. But what I need is comparison. All right. Okay, so let me look it up. Prolog is expression. That's not it. I know I cannot put n minus 1 here. Pretty sure about that. Too many open queries. Please complete some queries by using next. Okay, stop. Well, it says false. Abe is not 2 generations away. So it does use n minus 1. And if I have Homer, change this to 1, it is true. Okay, so I need to look this up, because I know that it can do something like this. It can count the number of ancestry steps. It's just a matter of, how I express the binding of the values of the variables. So I will work that out in time. So instead of, finish it, I will finish this program, when I get home. But the question now is, how does it get the job done? what would be the mechanism, that allows your Prolog as a programming language to do something like this? So let's go back to the slide because it is explained in the slide a little bit. Not this one, not this one, but this one here. So the basic mechanism behind Prolog is called substitution. So substitution is how we substitute one thing with another thing. I mean, that's not surprising. And this part here is just something that we talked about already. When we have the lightsaber is proper Jedi example, you can also see how if you want to use implication, it is saying the same thing as universally for all x in the universe, there exists a y in the universe such that x is a Jedi, x owns y, or in the example has, and y is a lightsaber. If all of these are true, then it implies that x is a proper Jedi. So this part we kind of talked about already. So now we single out, the phi, which is the portion without any quantification. So phi is only referring to this part here without the quantification. And substitution is represented by a set. Each item in the set is represented like this. X is the variable, and then the slash, and then we have the value that we use to substitute x with. So that's basically, so in this case, this set S is specifying that we would use Luke Skywalker as an atom to substitute for x as a variable, and at the same time, Anakin Blue is going to substitute y. Is that okay? That's how we express your substitution. And then the application of a substitution is just the original expression with the substitution set right next to it. So in this case, let me look at phi again. This is phi. It has a bunch of references to variables. This is the substitution. So to apply the substitution to phi, the result is whenever I see x, it is substituted by Luke Skywalker. Every time I see y, it is substituted by Anakin Blue. So the result of the substitution is going to be like this. So the result of the substitution is in return used to check with the ground facts. The ground facts are the ones that basically just state it's a Jedi, Luke Skywalker. Those are the ground rules. So once we get to this point here, where there are no variables, you can now check against the ground rules to see whether it is or it is not the case. All right. And Prolog is interesting in the sense that it is not only recursive, it also has what we call a backtracking feature. So that means once it has, so because there are different ways to do substitution. When we look at this phi here, x can be anything. It can be substituted by any atom in the entire universe, and so can y. So Prolog basically, has a systematic way of doing the substitution until it finds one that actually works. But you can also look at it from the procedural perspective. So when we look at Prolog from the procedural perspective, in this particular case, when I ask ancestor of, because I could not get ancestor and of to work the way that I wanted, so we'll focus on ancestor of at this point. So if I just ask whether Howland is an ancestor of Bart, okay, it confirms that it is the case. But internal to the Prolog engine, the way it gets the job done is it starts off with the first mentioning of the rule, and it will try to do a match. So in this case, it will try to do a match of parent of. It will check all the ground facts first. If the ground facts, if nothing can match this, then it moves on to the second rule of the same name. In which case, it will try to bind x with and z with something within the ground rules. And then once it finds a z Then it will check to see if I can to see if it can establish that y is an ancestor of z. If that doesn't work out, if the way it has chosen the x doesn't make the second part work, this is where the backtrack comes in. The backtrack comes back and say, oh, the way I chose x and z did not work out, and then it will try to choose another x z for the parent, and then this time z is different, and it will try to find whether y is a parent of z or not. So it has a built-in mechanism to do all the backtracking, which is great if you want to do something like this. So if you want to find out all the descendants of Howland, backtracking is a great feature. On the other hand, if you just want to do a loop structure and you don't really need it to backtrack, you just need to know one answer and not all the possible answers, then you don't want to do the backtracking. In prolog, there is a cut operator that basically says no backtracking beyond this point. So you can basically put a cut operator and specify, don't go back. If this fails, the whole thing just fails. Do not even go back to reattempt. So this is the weird part of prolog, because you can indeed write any code in prolog. If you can write it in, say, C or C++, in terms of general algorithms, you can translate that into prolog, except it's not going to look like programs that you're used to, because there are no loops in prolog. There are no conditional statements in prolog. Everything looks kind of like this. Are we still doing okay so far? Okay. So do you think we can find the shortest path between two vertices using prolog? I can see maybe because this is the first day that we actually see prolog. Okay. So how would you use prolog to encode a graph first? Okay, so the first thing is, how do we express a graph using prolog? It's okay for me to stack on the graph representation after this. So tell me again, what is a graph? It has G has two components. One is called V and one is called E. What is V?
Vertices.
Those are the vertices. So let's just say that we can make certain assumptions that the atoms are all vertices. So we don't have to name is a vertex plot, is a vertex plot. Okay. How do we express an edge? What is an edge in a graph? It's a two-tuple, and the ingredients or the first and the second component of the edge is going to be, are going to be
Two vertices.
the vertices. Okay, very good. So that means, if we assume all the atoms are vertices, then we can just say, there's an edge leading from a particular vertex to another vertex. So if we want to make a vertex of A to B, this is how we can state it. Okay, AB is an edge. Is that okay? So we can define a graph. So we can define a graph, where B goes to C. We can now say C goes to D. And then we can also establish alternative paths. So we can say A goes to C directly, and A goes to another vertex, say E, and then E goes to vertex D. Okay, so what I have done so far is to establish that I have 6 edges. A goes to B, B goes to C, C goes to D, A goes to C, A goes to E, and then E goes to D. So instead of finding the shortest path, if my objective is just to try to find out whether two vertices are connected by edges, how would we do that? Okay, in other words, if I want to say connects to, so I want to see if X connects to Y, what would be the non-recursive version of establishing that x and y are connected in the direction of x connects to y. Be pretty easy. Yep, just to make use of edge, right? Okay. So we say edge xy. All right. What about the recursive one? In other words, if the two vertices are not connected by a single edge, and instead there are multiple edges that eventually connect x to y, how would I express that?
Edge YZ.
Would be edge xz and then connects to z to y. Okay, so so we have edge xz and connects to z to y. Okay, well, we have seen this trick before, right? Because we saw this trick in ancestry of, and this is basically the same thing, same structure. Okay, the first part of the end is something that is atomic, it is a ground rule, and then the second part is the part that is recursive. But we have a problem here, because in the case of a graph, you can have a loop. So when you run into a loop, then we have a problem because now we cannot say, we cannot get out of the loop because it doesn't know it is in the loop already. Now, there are ways for you to do loop detection because prolog can handle lists. And you can basically use a list to keep track of vertices that you have seen already along this path. So if you see the same vertex again, you know you're in the loop, and then you can get out of the loop and say, nope, this is a dead end. Okay, go back and explore something else. But assuming that we cannot do that, okay, there are also other ways to do this, okay, but I'm going to talk about that. I will need the same mechanism to solve this problem in order to solve this problem of of dealing with loops. But right now, this graph has no loops. So that means, I can actually inquire whether certain vertices are connected or not. So now I can ask next to, well, we'll pick A and D because those two are indeed connected, and there are actually two paths connecting between these two. So I ask, are they connected? It will answer yes, and it will say yes again, and it will say yes again because there are actually three paths connecting vertex A to vertex D. Can you see the three paths? This is where, when things are not graphical, it's not quite as easy to visualize. Okay, so we got A, B, C, D. Okay, so A, B, C, D is one path. The alternate path is A to C, C to D. That's an alternate path. There's one more, which is A to E, E to D. So there are indeed three paths. Is that okay? But the next thing is if I throw an edge in so that we can have a loop, then this algorithm doesn't work anymore. It would not terminate. So if I just add an edge here, B back to A, now we have a problem because it doesn't know when to stop in this case. So if I ask the same question, it will say true, 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 because now you can loop that edge, and each time you loop through, it will find a quote unquote new path because it cannot establish repetition. Is that okay? So this becomes an infinite loop because it will keep looping through and keep saying true, 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 because it basically just has to loop from A to B, B back to A as many times as it takes so that it becomes a quote unquote different path. Because A, B, C, D is one path, A, B, A, B, C, D is one path, A, B, A, B, A, B, A, B, C, D is another path, and so on. But it cannot distinguish that those are basically the same thing, that we are stuck in the loop because we do not have the mechanism to track what vertices we have seen so far. Are we okay so far with this? So we got 5 minutes left, but I will leave this with kind of leave it with your thoughts. how many people know what is a database? Just a general concept. You don't have to know the queries and whatnot. Okay, so we got people who know what database is. So if you look at each table of a database, what is it? If you look at one row of a table in the database, how would you map it to Prolog?
The SQL database is a tuple.
It is a tuple, very good, but it's a confirmation, right? So you can basically use a ground rule like this one to express one row. Okay, all right. So how would you make a join operation? A join operation only requires a match of some of the items, some of the columns, so it can be expressed. Okay, but you can also, if you combine the concept of a database, let's just say that we have a way to take all the rows of each table in a database and express it using ground rules, such as the parent of or the edge inside a Prolog program. So now you have all the knowledge within the database, but expressed within a Prolog program. So what do you think are the possibilities in this case? You can do reasoning. So this is all about symbolic reasoning because that's what Prolog is built to do. So as long as you can encode the knowledge that you want the engine to execute for you in terms of the rules, now you can ask the Prolog program, which now has the facts coming from a database, and it can now perform reasoning within. It can do symbolic reasoning. I should be more specific, based on the facts that you have stored previously in the database. So if you know all the relationship, all the parent of relationship of the entire Sacramento, you can help people find their cousins. You can help people find people who are related. Not so easy if you're only using SQL queries. I'm not sure how many of you know what I'm talking about because you kind of need to know what SQL is first. And there are ways for SQL to do recursive relationship, but not to the extent or the flexibility that we can do in Prolog. So Prolog for the longest time is the AI language of choice in Europe and also in Japan. So if you look it up in Wikipedia, you will find references. So Prolog as an AI language. I'm trying to find the applications, like who used Prolog. And okay, let me see if Japan is here. Now that I did not know because earlier not in the class, well, actually, at the beginning before the class, we talked about video games. Sega implemented Prolog for use with Sega AI computer, released for the Japanese market in 1986. Prolog was used for reading natural language inputs in the Japanese language via a touchpad. Now that I did not know. That is kind of cool. Nope, it does not have any direct reference. So let's look up European. Okay, European AI researchers favored Prolog while American favored Lisp. So this is an interesting statement too, because back in those days, AI was limited only to symbolic processing. And can you guess why that is the case? I mean, the whole concept of neural network already existed back in those days. But why do you think neural networks never got any attention back in, I would say, 85, 84-ish?
Processing power?
Exactly. The lack thereof, okay? Because there were not a whole lot of processing power, and neural nets consume a lot of processing powers. So even the concept was already there, backpropagation, multiple layer of neural net, all of those concepts existed already at the same time when people focused on symbolic processing, there was just not enough processing power anywhere. And as a result, it was impractical because even though in theory it can be done, there was simply not enough processing power to make anything meaningful out of it. Symbolic processing like prolog or Lisp, those are easy to do, okay? Because symbolic processing is what traditional processors are very good at. And as a result, back in those days when processing power was not sufficient, symbolic processing was the only kind of AI that people could do. I should also add a little bit that Dijkstra's algorithm and the A-star algorithm were once borderline AI. They were borderline artificial intelligence. So, because it all depends on how you define artificial intelligence. Um, I will do one more thing and then we are done for today. So we look up Dijkstra's algorithm because I want to find out when it was invented. It has to be quite a while ago because the person who invented it, Mr. Edgar Dijkstra, passed away some time ago already. So I want to look for the year when it was invented. Well, there you go, 1956. So back in 1956, Dijkstra's algorithm was able to accomplish something that only people were able to do. In other words, it was right at the cusp of the problems that human can solve and the subset of the problems that computers could solve. So it's right at the cusp. So at the time when Dijkstra's algorithm was invented, I think AI was not even the term yet, but it was considered something to be AI because um, it was intelligent by the standard of 1956 that the computer was able to find the shortest path. What type of media do we have to store data back in 1956? Because I want to make sure that you all understand the context of all of this stuff here. So what was the method for people to store data in 1956? I mentioned mainframe computers, the black and white pictures. Those were in the 60s. Yep. Punch cards, yes. So if you think about it, okay, you are storing data using punch cards, as in paper with holes, okay? And yet your computer was able to find or was able to understand a graph and was able to find the shortest path between two vertices when everything were using stacks of cards to represent. That was considered AI back in those days. So the definition of AI is very fluid. It's really basically things that we would like computers to be able to do, but not quite yet. So a lot of solved problems were once AI problems, like playing chess. Okay, some of you mentioned that you were participating in the chess club. Playing chess was once an AI topic, not anymore. That problem is solved, and once it is solved, it is not AI anymore. All right. So I will look up and finish that program because I'm just kind of bummed that that program did not work the way that I thought it would work. So next time we meet, which is on Wednesday, I will have that program finished. And then we're going to get into finding the shortest path using prolog because that's also kind of interesting. All right. See you all on Wednesday. Yes, we do have class on Wednesday, even though Thursday is the first day of the break.
I actually won't be able to come